Okay, so for 2.2, we are talking about rates of change and derivatives. We are going to first look at the average rate of change and then use that to talk about instantaneous rate of change. So if y is f of x, then the average rate of change of y with respect to x is given by the slope. So m equals the change in y, which you may have seen is delta y over delta x, or the change in y over the change in x. It's rise over run. Or lastly, f of x2 minus f of x1. So ending y value minus beginning y value over end x value minus beginning x value. Okay, so let's find the average rate of change, which is just the slope between these 2 points for this function f of x equals 3x plus 8. Between x1 is -2 and x2 is 1. So we're going to figure out what f of x2 is and what f of x1 is. So f of x2 would be 3 times 1 plus 8, which is 11. F of x1 is 3 times -2 plus 8. So it would be -6 plus 8 is 2. And so the change in y over the change in x, or we could call that f of x2 minus f of x1 over x2 minus x1. This would be 11 minus 2 divided by x2 is 1 minus a -2, that's x1. So you're looking at what, 9 over 3, which is 3. And that is the average rate of change for f between -2 and 1. All right, so then graphically, you can do the same thing. Look at x1 equals -3, so we're up here, and x2 equals 1, so we're down here. And we're looking at the slope of this line. So you're going to do the same thing, f of x2 minus f of x1 over x2 minus x1. So that is f of 1 minus f of -3 over 1 minus -3. So up top, f of 1 is -1. F of -3 is +3. And then 1 minus 3 is 4. So we have 1 minus -3 is 4. So we have what, -4 over 4, which is -1. And that is the average rate of change between -3 and 1. This is, y2 minus y1 over x2 minus x1. Did I write that anywhere? No. y2 minus y1 over x2 minus x1. Okay. I would like for you guys to try these. You should be able to do them just with those examples. These first two you're going to do with the function itself. And then this last one you're going to look at graphically. Find where x1 is -2, so that would be this point down here. And x2 is 0, so that would be this point. And you would be looking for the slope of that line. Okay, so I guess I could tell you what those answers are so you could check yourselves. Let's see, what are those answers? This one is 0.45 repeating, or what is equal to 5/11. This one is 2/15. This one is 2. So give those a shot. The line that I keep drawing that's connecting those 2 points is called a secant line. The average rate of change is the slope of the secant line. The average rate of change can be used to estimate or approximate the instantaneous rate of change at a point. So let's see. In this problem number 2, we're looking at the average rate of change between x1 equals 3 and x2 equals 3.5, and we got 2/15. So how could we improve that approximation of the instantaneous rate of change? we would just get closer, get x2 closer to 3. And if you continue to do that, to squeeze in and in, get closer and closer to that x1 value, you'll get better and better approximations of the instantaneous rate of change. So the instantaneous rate of change is exactly the limit as the change in x, so delta x goes to 0 of the slope, so delta y over delta x. So the space between x1 and x2, this is getting smaller and smaller. And as you take the limit, as that thing goes to 0, that change in x goes to 0, you're actually going to find the instantaneous rate of change. So if we look at some examples of that, we have this function y equals x squared. We are going to try to find the instantaneous rate of change, or we're going to approximate the instantaneous rate of change at x equals 3. We are going to use the average rate of change between two x values, but those x values are going to get closer and closer together. So x1 is 3, x2 is 4. If we do here the average rate of change, we're looking at x squared, so 16 minus 9 divided by 4 minus 3. So you have, what, 7? If you plug in 3.1, just trust me on this, if you plug in 3.1, you're looking at 9.61 minus 9 over 3.1 minus 3, which is 0.61 divided by 0.1, and then that is 6.1. And if you do this one, looking closer, then making that change in x even smaller, 1/100, you're looking at 9.0601 divided minus 9, sorry, divided by 3.01 minus 3. This eventually, this gives you 6.01. Okay, so if you're looking at this, what's the pattern here? As we get closer to 3, right, these values are getting closer to 3. These values seem to be approaching 6. And that is the limit as the change in y, the limit as the change in x goes to 0 of the change in y over the change in x. That is 6. That is the instantaneous rate of change. So I want to show you this like model of this in Desmos. So this is some function here graphed, but what I want you to notice is that we have these points here and here. So those are two x values. And what we're going to do, basically, let's fix this one. Let's fix it there maybe. And then we're going to basically drag this guy, get him closer and closer to that x value. So the change in x is getting smaller and smaller. So you have this secant line, and you have these secant lines, and as you that difference in x gets smaller and smaller, that secant line is going to get closer and closer to what is called the tangent line, and that is the instantaneous rate of change. So, oh, now they're just stuck together. I don't know how to get those apart. Oh, there we go. So secant line, take the limit as that change in x gets closer and closer to 0, and then boom, when that is actually the instantaneous rate of change when you take the limit as that change in x goes to 0. So the rate of change, the average rate of change is the slope of the secant line. So if you're looking at, like, I don't know, you want to look at here, you can tell that the slope here is 0, right? So this would be the, I'm not going to tell you what that's called yet. So if you look at that, that is the slope there, you can tell is flat, the instantaneous rate of change there. But what you would be looking at for the, you're taking some value here, you've got this line, that is the secant line. And then you get this one, and here's the secant line. And you get this one, and here's the secant line. And you can tell that those slopes, they're getting flatter, right? They're getting closer to that instantaneous rate of change, which is 0. That slope is 0. Okay, so as x2 gets closer and closer to x1, and we take the limit here, the limit of those secant lines, then the new line is called the tangent line. So I have it on the graph above there, and let's see. The slope of the line is the instantaneous rate of change, the slope of the tangent line. Okay, and you can do this anywhere, like the tangent line here would be like this. Basically, you know, when someone says they go off on a tangent, it's because they're talking about something that's like closely related, but like maybe only has one point of being related, and that is I can't draw a line, sorry. So like it's tangentially related in the sense that it's connected at this one point, but nowhere else. So that's the tangent line is sort of the slope at the particular point where you are. The derivative, sorry, this number is also called the derivative. So the instantaneous rate of change is the derivative. And that is the slope of the tangent line. So if you have f of x, y equals f of x, the slope of the tangent line at a, b is given by the limit as the change in x goes to 0 of delta y over delta x. This is equal to the limit. This is formal notation as h goes to 0 of f of x plus h minus f of x. So that's x2 and x1 over x plus h, that's x2, minus x1, which is just x. So this looks a lot like what we were just doing with the average rate of change. It's just here you're looking at that x2 getting closer and closer to x. So h is getting closer to 0. And then if you actually do this, you have just simplifying the bottom. The limit as h goes to 0 of f of x plus h minus f of x, and this is all over just h because the x's cancel out. So this number is called the derivative of f of x at a, at x equals a. So talking about f of x and f prime of x, this will often be written as f prime of x, that's the derivative. So f of a is the function value of f at a, which is what you knew before you came in this class, or is the height of the function at x equals a, the y value, right? F prime of a is the derivative of f at a, which is the slope of the function at a, the slope of the tangent line, which is also the instantaneous rate of change at x equals a. Okay, so then we have this f of 3 is 14 and f prime of 3 is 7 for this function f of x equals 2 plus x squared. So interpreting that meaning, the height of f at x equals 3 is 14. The slope of the tangent line at x equals 3 is 7. So that's the rate, the instantaneous rate of change at x equals 3 is 7. Okay, so that means it's positively sloped there, it's increasing at a rate of 7 per move. Okay, so suppose f of x denotes the production units for input x and labor units man hours. Suppose f of 500 is 2,000 and f prime of 500 is 3. What does f of 500 equals 2,000 mean? And what does f prime of 500 equaling 3 mean? So f of x denotes production units for input x and labor units man hours. So after 500 hours of work, man hours of work, 2,000 units have been produced. Production units is 2,000, input is man hours. So after 500 man hours of work, 2,000 units have been produced. And then secondly, we have this, okay, f prime of 500, f of 500 equals 2,000, f prime of 500 equals 3. So this means the rate of change of production at 500 hours, moving to the next hour, is 3 units per hour. So the rate of change of production at 500 man hours is 3 units per hour. So the increased production, if X is increased from 500 to 501, should be 2003. You're looking then at basically at F of 501 would be approximately 2003, because the rate of change is 3 units per hour at that point. So moving from 500 to 501 means you should have increased from 2,000 units to 2003 units. Okay, then let's see, average prices for new construction have steadily risen in Charleston, South Carolina since 2000. Suppose f of x equals 3,000x plus $72,000 is the cost of a new house of 2,200 square feet, and x is the number of years since 2000. F prime of x equals 3,000. We're to interpret this. So the instantaneous rate of change, x years after 2,000 is $3,000. So x years after 2,000, the instantaneous rate of change is $3,000. So the cost of the house increases by $3,000. So f of 3 being $81,000 makes sense. This is 3 years after 2,000. Then you should have 3 times 3, which is 9. So you should go from 72,000 plus 9,000, which is 81,000. So the cost in 2003, the cost of the house, this same house, that's 2,200 square feet, is $81,000. Okay, so this last example, we have miles, f of x is the number of gallons of gas used by a car after it has traveled X miles. So suppose the car gets 20 miles per gallon. What is f of 100? F of 100 is the number of gallons of gas used by a car after it has traveled 100 miles. So if it gets 20 miles per gallon, we've gone 100 miles, we use 5 gallons of gas. We're looking at 100 miles divided by 20 miles per gallon. So this would be 5 gallons of gas, which is f of 100. Is f prime of 100 positive or negative? So is the rate of change of the number of gallons of gas being used by a car increasing or decreasing? And is it positive or negative? It should be positive, that rate of change, because you should be using more gas the further you travel. Okay, and then last but not least, would f prime of 100 be greater for a subcompact car or for an SUV? So this is the rate of change of numbers of gallons of gas used. Rate of change of numbers of gallons of gas used. The subcompact car should be less than the SUV because it should be using less gas overall. So that is the pretty much everything for section 2.2. Let me know if you have any questions. I would be happy to help you.